Time is fully allocated, right?
Yes, we have 5 minutes.
So we probably don't actually need 15 minutes for the beginning. We probably don't need 15 minutes for ourselves, so we can get back a little bit. I'm just wondering how long to wait for the room to fill. Hey, folks, please start finding your seats. Also, you'll see on the projector the URL for the Etherpad. If you feel so moved to help us with minutes, that would help us get started with the meeting. Please raise your hand if you're willing to help with minutes. The chairs can't do it because we're busy running the meeting. Please volunteer. While you're thinking about volunteering and the room is filling in, I know that somebody who's currently about to sit down is going to volunteer to take minutes. That's the punishment for coming in late. You've all already seen the note well several times. You will see it more times. If you haven't already read it, you actually should. It pertains to what may or may not be your intellectual property and what your obligations are with respect to disclosing said intellectual property in the IETF. I'm not your lawyer. If you care about this, maybe you should talk to your lawyer about it. You've already clicked on something that said you were agreeing to it, so it's good to know what it says. And now we're back to needing to see a hand for at least 1 minute taker. You can tag team. By the way, it's also helpful, especially if you are a person who comments at the mic and if you have a hard name to pronounce or spell, and if you don't like to see your name misspelled, to pull that Etherpad open and correct the spelling of your name in the minutes, or to get on the Jabber Room and correct the spelling of your name in the Jabber Room. Or if you know the spelling of someone else's name, to do the same. It's actually remarkably helpful. A volunteer, please, for minutes. By the way, you're not obligated to use the Etherpad for minutes. You can also, take them in longhand on a yellow pad, or, use your favorite text editor or whatever else you like. You're not also obligated to take down every single thing that's mentioned. Mainly what we want is to capture questions and answers. There's certainly no need to transcribe slides. Thank you very much. So, onward. sorry. Okay. So, since last time, we have an RFC published, 7855. So onward to more RFCs. We have use cases in working group last call. That's end of that last call is coming up pretty soon. So please do go read, comment. And this is a good opportunity also to remind the group that when we have working group last calls, it is very helpful to hear from members of the group that you have read the document, that you think the quality of the document is actually good enough to publish, that you think the document should be published. If you don't say anything, the chairs are not going to assume that you support publication. So a working group last call that gets no response generally is not going to move forward. Likewise, a working group last call that gets a few, +1, +1, +1 also makes it a little bit difficult for us to say that there's, strong and clear consensus for publication. So actual feedback and clear feedback is pretty much imperative for moving a last call forward. So next we have a bunch of drafts that are ready to start working group last call. A whole pack of pretty much use cases documents and related that we've been asked to basically the IESG has provided us with feedback that they would like to deal with this stuff all at once. So we will do that. And in addition to those, a couple others that are also ready for last call. So there's going to be a bunch of last calls. You might remember last year we did a bunch of last calls in August. Well, I guess we're going to do another bunch of last calls in August. And for the same reason that we extended the, beyond the sort of traditional 2-week time last time, we will do the same again this time to provide people with enough time to review a whole pile of documents and also to respect the fact that many of our colleagues will be taking extended summer vacations in August. And if you would like to volunteer to be a document shepherd, please get in touch with either one of the chairs. It's actually a great way to get involved in the whole IETF process if you haven't been, or if you have been, you know how much we'll appreciate it if you volunteer. And then we have a request for working group adoption for any cast segments, so which, and all of these working group last calls and adoption calls will begin basically as soon as I get a free minute to send out a bunch of emails after the meeting. So, you want to take over?
Yes, so as John said, to improve the quality of the document, we need review. So during the last call, we really would like to have review on the documents, review on comments on the documents. And also you can review related documents in other working groups, such as ISIS, OSPF, PC, and IDR. So it's important for the quality of the document. And if you would like to have comments on your working group documents, you should also review the other working group documents to share the load. Last slide. There is a new tool in the data tracker which can track the draft related to the working group documents. So it tracks working group documents, RSC. And also we can track any document based on the matching on file names. So currently it's tracking documents starting with draft, something spring. And also all the draft with segment routing in the name. So it's a nice way to track the draft in other working group, such as again ISIS, OSPF, PCE. It's possible to extend the matching with other names. So if you want to have the tool extended, it's possible. So send a comment to the chair. And here we have the agenda. We have full agenda today. So we will ask for each speaker to respect their time. Okay. Any comment on the agenda? So we can start with Stefano.
Anyway, I think it's going to be pretty short. So hi, I'm Stefano from Cisco. An update on the different drafts. As John just said it, we have our first RFC. So thanks to everybody who contributed in terms of authorship, in terms of editing, and in terms of review. The architecture draft, we had, I think, a couple of submissions since last IETF. So in short, we added clarification text, we updated references, and we added two sections, the security and the manageability sections that were missing in the draft. So this makes this draft even more ready to working group last call. Same for the MPLS instantiation of segment routing. So the segment routing MPLS draft, clean up the text, added clarification text on the mapping server usage, and also some text has been put for the security and manageability, so to have the draft ready for working group last call. The LDP interop draft, this is where I think most of the work has been done in the last month or two. The draft has been kind of reorganized. The sections have been reordered. I think it's much better for the clarity. We added text on first on references, because the draft refers to many other technologies, and so the references were missing. And we added clarifications on FRR, on the use of targeted or directed LDP sessions. The terminology was not, I would say, correct in the text. Data plane verification, mapping server, and also some explanatory text on the interoperability between segment routing and LDP when LDP is configured in ordered control mode or independent control mode. I mean, the two modes that LDP has. Also added security and manageability sections. And I don't know if Sasha is in the room. Many thanks to him for the review that he made on the draft. And I think also this document is ready to go for working group last call. Still in the architecture draft, the conflict resolution draft. I mean, we have a next point in the agenda, so be ready to enjoy the show. And I will skip this one. The other the use cases draft, as John also already mentioned, we have the MSDC, the central EPE, and the IPv6 use cases. Those drafts have been very stable, no changes. At least from the IPv6 use cases, we know the authors resubmit recently a version that is ready to be sent for working group last call. And I think in the resiliency use case, you gave also an update on this, John. The authors had to answer. I don't know if they did on the last comments. Not yet. So this will probably have to be updated before sending it. And we still have two individual submissions that also have been pretty stable: the recursive info and the large-scale interconnect. I mean, the authors believe those documents are ready to be adopted as working group documents. That's pretty much it. Yes. Questions?
Thank you.
Thank you.
Les. Here's your talking stick.
My square.
Don't step outside of the square and everything will be okay.
Okay. Okay, I'm Les Ginsberg, my esteemed co-authors on the draft. I've got a lot of slides here. I'm going to go through a bunch of the first ones rather quickly because I think we've covered most of this material either in my last presentation or in other on the working group list. So briefly, why are we doing this? Because when you have conflicts, the problem is a globally scoped problem that needs to be solved. It can't be solved simply by local configuration or individual choice. So we need to establish a consistent policy so that all nodes in the network, given the same database, will come up with the same answer. Since Buenos Aires, the draft has become a working group document. We had an agreement on handling overlapping sRGBs. That has now been put into the document. And we also issued a V1 that included some changes to the conflict resolution based on the input we received to date. But as far as conflict resolution, this is still very much open. It's still very much being discussed. This is briefly the handling of sRGB entries. I put this in the slides to some extent. You can go to the slides since they're loaded up line and see all this. This has been previously presented, so I'm going to move along. This is the specific language that talks about how to handle the overlapping sRGB ranges. We made supporting updates to the SR MPLS draft. Okay, for conflict resolution, it's still true that we have not achieved consensus. The configuration is distributed, so you have local configuration for your prefix SIDs, and if you're acting as a mapping server, then you're going to do local configuration for the mapping server. But you can certainly prevent conflicts at configuration time within your local configuration, but you can't prevent conflicts between the configurations on different nodes. So that's the problem that we need to solve, and we want to do this by applying a consistent policy. This is the general definition of the mapping entry. I think since the last presentation, we've also added topology and algorithm as additional attributes. There are two different types of conflicts. You can have what we've termed a prefix conflict, when you have different SIDs assigned to the same prefix. Or you could also have a SID conflict where the same SID has been assigned to two different prefixes. The prefix conflicts are scoped by a given topology and algorithm. SID conflicts are across all topologies and all algorithms because the label space on your router is shared among all of these contexts. To achieve consistency, obviously you must have the same database on all nodes. If you don't, no definition is going to achieve consistency. Whether a particular SID has been configured locally or it's been configured on some remote node can't be taken into account, because obviously if each node prefers what's locally configured, we're going to end up with different answers on different nodes. So priority is whatever the algorithm we end up achieving consensus on, the priority is based on the content of the advertisement, not where it comes from. There are two sources of data. One is the prefix reachability advertisements that have prefix SIDs associated with them. And those come both from your local configuration and the prefixes that you advertise. And of course, they come from the remote entries that you receive from your protocol peers. In the case of local, depending on what your configuration CLI may be, you may be able to configure SIDs for prefixes that you don't actually advertise. If that's the case, you cannot consider the information that you don't advertise in your conflict resolution database because it's not known network-wide. Similarly, with SRMS advertisements, you can only consider what you actually advertise if you're acting as a mapping server. This is the preference rule that's currently in the draft. As you'll see as I go into the presentation, we're suggesting an alternative with a change in the preference rules. I'm going to go into that, but this is what's currently in the draft. And what's probably key here are the first two rules. The draft currently says we prefer prefix advertisements over SRMS advertisements. And related to that, we prefer an entry with smaller range over an entry with larger range. There are three policies that are currently mentioned in the draft. Again, we have not achieved consensus. The goal here is to end up with one policy, one preference rule. So the fact that the draft currently has multiple doesn't mean that we're going to propose multiple solutions and people configure which one they want. No, we're trying to move to one, but we haven't achieved consensus yet, so we're keeping discussion of multiple policies in the draft. The first one is ignore, and I've crossed it out because it isn't getting very much support in the discussions that we've had so far. So what we're really talking about actively are the bottom two, which currently in the draft it's called quarantine. It could also be referred to as per advertisement. In this policy, you use the preference rule to compare two advertisements. You decide which one wins. The one that loses is excluded. We do not use any of the entries in that advertisement. The ignore overlap policy, which could also be called perfect, you use a preference rule on a perfect basis to decide which one is the winner. For if you have an entry with a range greater than 1, then you will not if the entry in that particular advertisement loses, you do not use that particular entry, but you still may use other entries in that same advertisement. So there's a working example, and again, this example is not in the current version of the draft. This example actually was suggested by Bruno, and we've started to use this. We think it's probably a more practical example than the examples that are in the draft. So consider that you have partial SR deployment. Let's say you have 50 nodes that are SR capable, you have 50 nodes that are not SR capable. The 50 SR capable nodes are going to be advertising their SIDs in prefix reachability advertisements. You are going to have one or more SRMSs in the network to support the non-SR capable nodes. Because the range of addresses that are associated with the SR capable nodes and the non-SR capable nodes are not necessarily contiguous, the mapping server is going to advertise SIDs for the full range for all the nodes in the network, whether they're SR capable or not SR capable. So in this example, we have 50 nodes, 192.0.2.1 through 192.0.2.50. Those are SR capable. They're advertising their corresponding SIDs between SID number 1 and SID number 50. And we have 50 SR incapable nodes. And the SRMS advertisement is for a range of 100, covering both the SR capable and the SR incapable nodes. This is the correct configuration, if you will. Now we're going to look at some examples where some misconfiguration occurs. We use two terms. One is the active policy, that essentially are the entries that are declared the winner based on the preference rule. And the ones that lose are part of the excluded. And in the examples, we're going to detail how many prefixes are in the active policy set and how many prefixes are in the excluded. The numbers may not intuitively add up to you, And the reason that they may not add up is because we're counting the number of prefixes which are covered, not necessarily the number of entries which are included or excluded. So sometimes it may look a little bit non-intuitive, but I believe it's correct. If it isn't correct, please send me an email, I'll correct it. So here's the first example. The misconfiguration here is with a particular prefix advertisement. For 192.02.12, the correct SID was supposed to be 12, but it's misconfigured to be 52. So with quarantine, you end up with, because we prefer the prefix advertisements, we accept all of the 50 prefix advertisement entries. Because there's one entry for 192.02.12, which conflicts with an entry in the mapping server entry, we exclude the mapping server entry. And so we end up with 50 prefixes covered in the active policy, 50 in the excluded. If you use ignore overlap only, then we end up with 99 prefixes covered in the active policy and 1 in the excluded policy. And I'm going to move through this. Again, if somebody thinks there's an error in the slides, I'll certainly correct that, but I don't think any error made is substantive, so it demonstrates what we want to demonstrate. Here's another example. In this case, we misconfigured the starting address in the SRMS entry. It was supposed to be 192.021. It is 192.020. And you see the results are again with quarantine. We end up with 50 entries in the active policy, 50 in the excluded. In the case of ignore overlap only, we end up with 98 in the active policy and 2 in the excluded. Here's the third type of error. For the SRMS entry, we misconfigured the SID. The SID was supposed to start with 1, but it starts with 101. Again, quarantine ends up with 50 active, 50 excluded. Overlap only ends up with 100 active and none excluded. And again, I'm talking here about how many prefixes are covered. Obviously, there is an entry in the excluded set, but that particular IP address still has a SID because of we're using the advertisement from the prefix advertisement. Here's a fourth example. In this case, we misconfigured the SID in the SRMS entry, but we have redundant SRMSs in the network, which is something that's highly recommended. So I think this is a very practical deployment example. And what you see here is with the redundant SRMSs, the quarantine ends up, actually both policies end up covering all the prefixes. So clearly there are a number of examples here which demonstrate that the ignore overlap only does quite a bit better in terms of prefix coverage than the quarantine. We decided to take a look at what would happen if we changed the preference rule. Instead of preferring prefix advertisements over SRMS advertisements and preferring the smaller range, what would happen if we preferred the larger range? So I've just highlighted the differences here. The rest of the tiebreakers are the same. And we run through the same examples. And what we see here is quarantine now does just as well as ignore overlap only. Here's the second example, same result. Third example, same result. Fourth example, which is actually unchanged in terms of its coverage. It wasn't really affected by the change in the preference rule. So here's a summary. If you have a range preference for a smaller range, then ignore overlap does quite a bit better. But if you have a range preference for the larger range, then both policies have the same results in this set of examples. So what are some overall goals here? I think there are two goals. One is that we would like to minimize the complexity. The problem that we're trying to address is a transient problem. There's a misconfiguration, in some period of time, which may be minutes, it may be hours, it may be days, the misconfiguration will be corrected. But during that period, we need a policy to try to decide what to do until this misconfiguration is corrected. Given that it's a transient problem, it seems desirable to minimize the complexity. This means that implementations will be simpler, they're less likely to have bugs, they're less likely to have interoperability problems. Two implementations not necessarily getting the same answer with the same data. Second goal is to try to maximize forwarding. Yeah, we have a misconfiguration, but it would still be nice if we could forward as much traffic as possible. Remembering that in the case of a misconfiguration, as long as you can get nodes of the network to agree on what the SID is, it doesn't really matter whether that SID is the SID you intended to be used. As long as everybody agrees that it's the same SID and it doesn't conflict with anybody else, then you're going to get successful forwarding. So the evaluation here is, as far as complexity, a quarantine implementation is less complex. As far as maximizing SR forwarding, the ignore overlap only is the best, but if you change the preference rule, we can get quarantine to come pretty close to the same behavior as ignore overlap only. From a deployment strategy, if you use redundant SRMSs, which is recommended in the existing drafts and is a sound policy, that alone, regardless of whether we end up getting consensus on quarantine or ignore overlap only, makes a big improvement. It particularly improves the results of quarantine. For ignore overlap only, doesn't make much change. If you use larger range, which as we've shown in these examples, helps the quarantine policy perform nearly as well as the ignore overlap. This says that you want to use an SRMS not just as a vehicle to handle partial deployment of segment routing, but you actually want to use it as a global provisioning tool, even if your network is fully SR capable. You don't have to do that, but if you're worried about what happens if I do have a misconfiguration, how big an impact is this going to have on forwarding, then it suggests that you want to use the SRMS as a global provisioning tool, because the likelihood of ending up with a lot of prefixes that can't be forwarded because of the conflicts introduced by the misconfiguration is less. So next steps, and this is the point that I wanted to get to here, I'm really hoping we get some input here. The debate at the moment is, should we go with a quarantine approach or should we go with an ignore overlap approach? Really would like to get input, particularly from vendors, but from anybody, on their view of the relative complexities of implementing these two strategies. Second thing, we want input from network operators. Again, not just network operators, but network operators are obviously very concerned about the impact on traffic. How do you see the two strategies playing out, and how important are the characteristics of the two strategies to your network planning? One other point, there has been some discussion on the list about incorporating the use of weight to identify a preference between SRMSs and or potentially individual SRMS advertisements. This is not in the draft and it's not in the presentation because there hasn't been a clear decision made on the scope of weight. Should it be done per advertisement or should it be done per node? There are going to be changes required in the protocol extensions for segment routing in order to support this. Until we decide the scope of the weight. We didn't know exactly what to put in the draft, so we haven't done it. But it's pretty clear that we are going to incorporate weight. I don't think that's going to have a significant impact on the choice between the two policies. It's just a heads up that we haven't forgotten about this, but it just wasn't, we didn't have enough information yet to put this into the draft. So next thing we're going to do clearly is spin another version of the draft, but at this point, we really want to get more input. And so I'm going to stop and wait for the line of people to step up.
No line, but just me, Robert Rashu. So is it in scope if to treat SRMS as an SDN controller and override IGP with SIDS, for example? I'm asking this just being in I2RS 2 hours ago, but just curious if that's not the factor to decide which solution to choose.
I'm not sure I fully understand your question.
So if I would like to override my SID distribution with SRMS, override what is IGP distributing, wouldn't that have impact on your choice?
Well, I think what it has in it, no, I don't. Well, that's a matter to get input. What it clearly impacts is how you utilize SRMS. If you're worried about, and again, if you never make a mistake in your configuration, or you're not particularly worried about the impact of these mistakes, you can use whatever policy seems best to you. But I think if you're trying to minimize the impact of a misconfiguration, we see that you preferring the SRMS entries allows a simpler implementation to do just as well as a more complex implementation. And so that says, I want to use SRMS as a global provisioning tool, which is not the way SRMS was initially envisioned. It was envisioned as a transition tool to full SR deployment. But I think that has evolved. Again, it's probably operators who should provide input on this. To me, I can see advantages to using an SRMS completely independent of conflict resolution. You go to 2 nodes or 3 nodes, you do your SID configuration. It's in a central place. You don't have to go to every node in the network, figure out what prefixes that node is advertising, what the SIDs are, make sure that it doesn't conflict with what you assign to another node. You've only got 2 or 3 places. So that's what it seems like to me, but
no, but my point is it wouldn't be misconfiguration, right? It would be on purpose configuration of different values as comparing IGP to SRMS. That's the whole point, right? It would no longer be a misconfiguration.
You are saying somebody deliberately puts different values into SRMS?
Yes, just to override IGP
and what
distribution.
is the functional value of that?
Well, to control the network from central controllers.
But why do you have to configure different values than you would have if you configured locally?
I realize that it's a little crowded, but it really helps the remote attendees to hear what you're saying if you make your comment into the microphone.
Robert, when we talk about SRMS, we talk about ISIS and OSPF protocol extensions. So your question is, can I use some of the extensions I worked out for ISIS in order to override other extensions that I made for ISIS? So this is the context of the SRMS. I think your question goes way beyond that context and say, what if we defined the functionality of the SRMS, maybe not using ISIS and OSPF, using something else, that will come and configure my box with the right SID. And I'm perfectly fine with that. And I think it would be a very good idea to remove that load from the routing protocol and do it on the management layer rather than in the routing protocol. Yes, but not in this context, because this is inside ISIS, inside OSPF. So the outcome of that draft will then dictate the behavior in the ISIS and the OSPF spec. So that's different.
So you are right, but we will not modify SRMS again, right? That's the whole point. If we do it now right way, we will encourage the kind of use cases I may envision later.
I rely on your imagination to find a new word and a new acronym.
Bruno de Crane, Orange. Two comments, 2 points. First on network availability. That was my main comment from day one in November. So many thanks for the improvement in the slides. Much more improvement to take into account and to measure the impact on the network availability. And as a consequence, the solution has been or is proposed to be revised to improve the availability. So thank you very much to all the authors for the work, for the improvement. Yet the slides are very different from the draft.
Correct.
So I'm happy with the slides, but I'm not happy with the draft.
Yeah, well, so a lot of the changes, what we're presenting in the draft is based upon a lot of very recent input. I'm sorry, what we're presenting in the slides. So it's not reflected in the draft. I hope I made that statement at the beginning. The intention is to spin a new version of the draft, which is consistent with the slides. But of course, that's not the end of the story because we haven't achieved consensus yet. So what we really want to go is to get a version of the draft that has consensus.
Yes, but it would be good to have a new version of the draft which reflect what has been presented today and which give more emphasis to the impact on network availability.
You know, we definitely will. I guess what I'd like to do is maybe wait a couple weeks, see what kind of input we get, and spin a new version. If we don't get a lot of input, we'll spin a new version based upon what you see in the slides, and then we still have to get more input.
So in which case you need to make clear that you want input from the slides and not on the draft, because they are very different.
Yes, I will repeat that again. We want input on what's presented in the slides.
Okay, so we will skip for the time. I will skip my comments on the draft, which I think will be updated. Another comment, if you can move to slide 19, please. Okay, so with the new policy, the mapping server is preferred by design over the prefixed, always. So at this point, for network operator which use LTP interworking, there is little to no point to configure a seed on router because the advertisement will just never be used. So it's a change. I'm not saying it's bad or good, it's just a significant change compared to what would be prepared to configure and deploy. So maybe this could be said or highlighted. Another comment, since with quarantined, you are going to disregard the prefix seed. I mean, in your quarantine, the prefix seed. I was wondering what you want to do with the flags which are advertised with the prefix seed and which may be different from the flags advertised by the mapping server. Specifically from the penultimate popping point of view, would each node be responsible for choosing to use PHP or not? Or is it going to be the mapping server which is going to say every node needs to do PHP or every node needs to not do PHP, so the ultimate popping?
So
how are you going to handle that?
So if you're talking specifically here about the attached flag,
No, the penultimate popping.
no, I understand that.
Okay.
Okay. But you're saying, okay, if we start using SRMS entries, what's significant in the SRMS entries is the attached flag.
All the flags.
The only flag you have in the SRMS entries is the attached flag.
The only flags which is currently used is the attached flag. The other one have to be ignored. But
Yeah, so anyways, the point I'm trying to make is, so speaking here specifically about ISIS, we introduced the prefix attributes sub-TLV, which has some redundancy with flags that are currently in the prefix SID sub-TLV. And we have stated, it's already in the draft, that the long-term plan, we obviously have existing deployments that we have to worry about, so we have a transition plan. But the long-term plan is the flags will be deprecated from the prefix SID sub-TLV, and you have the prefix attributes sub-TLV, which will allow you to tell whether an advertisement is local or not local, so you will no longer need the attached flag. As far as PHP behavior, it will be clear based upon the prefix advertisement, even if you're still using the SRMS advertisement to get the SID.
Did you say something about PHP? No?
Yes?
Penalty method popping?
Yes.
Notice there is a specific flag which say, so yes, there is an attached flag to say I'm the owner of the prefix. So that one thing.
The
attached.
owner of the prefix is determined by once support for prefix attribute sub-TLV is deployed, you no longer need the flags in the prefix SID sub-TLV.
Okay. So one thing is to say I am the owner of the prefix. And another different thing is to say I want PHP penalty method popping of the MPLS label down by the penalty method up or not. And it's a different thing. So that flag is only in the prefix SID advertisement. So if you disregard it.
So I've forgotten, is the PHP flag in the prefix SID or is it in, okay, we'll have to take a look at that.
Okay. Because if you disregard the advertisement of the prefix SID, how do we understand?
So I think the flags in the SRMS entry to me have always been a bit of a hack because they require manual configuration on the SRMS server of what's being advertised by other nodes in the network. So to me, the correct solution is to have the information based upon what the node which is actually advertising the prefix and what he says. So if your comment is, well, we still need the prefix SID sub-TLV in order to get this flag to know what to do with PHP, then I think we can say, even though we're not using the SID in the prefix SID sub-TLV, we'll use the flag.
Okay, so you don't really completely disregard the mapping, the prefix SID advertisement.
All we're trying to resolve here is SID conflicts. There's been no discussion about flag conflicts.
So, but it would be good to detail how you handle the flags. Because currently you said I disregard. Currently you said I disregard the IGP advertisement.
For the purposes of the SID.
Yes.
I think for this discussion, I would like to constrain that statement to the SID.
So it would be good to update the draft to reflect.
Fair point.
Another comment.
Hey, Bruno,
Yeah.
there's two other people waiting to make comments, so maybe keep your comments, stay in line, but let these guys.
So regarding Shraddha Juniper Networks, so regarding the change in the preference rule, the latest one says larger range wins. So in the OSPF draft, I think the latest has a statement where if there's a prefix range advertisement and there is a prefix SID advertisement, then prefix SID advertisement is preferred. So I think that there's going to be conflict, and how are we going to handle it?
Yeah, so both the ISIS draft and the OSPF draft have that statement in them. I think we have agreement that we want, first of all, we want to take those statements out of the IGP drafts because we want all of the stuff related to conflict resolution in the conflict resolution draft. And then I think the disposition of what we say depends upon which preference rule we end up agreeing upon.
Rob Shakir, Jive. So one observation to expand on something that Bruno said, if you just ignore the prefix SID and you use the SRMS entry, doesn't this rather compromise the effectiveness increase the risk of actually ever turning off your SRMS? So if I introduce, I've got a network, I have one node that supports SR in it, I turn on SRMS because that gets me interop. Essentially, as I go around and provision all my other nodes, that config does nothing. So I don't actually know that it works. And I have this big risk event where I have to turn off the SRMS. Probably not ever going to do that at that point. But I think it decreases the availability of the network if you don't do it, right? Because now you have to rely on a subset of N nodes that are acting as SRMS rather than every node advertising for itself. So I can see the effectiveness for this problem, but I think there are some operational gotchas that we might want to just kind of think through to say, well, is that a sensible way to be pushing operators?
Sure, and I think that's the kind of input we want to get. It was from an operational perspective. Do you see using an SRMS in this way? Because clearly the rule on the right sort of pushes you in it doesn't force you, doesn't absolutely force you, but it pushes you in the direction of saying, I should be using SRMS. Is that a direction that you want to go?
Other than this work, I wouldn't be thinking about using SRMS at all.
Okay.
Hendricks, Nokia. Yeah, so we prefer the per prefix one because it has better coverage at the end of the day in case of impact, right? So as a vendor, our preference is not a quarantine, but the other approach, given it in certain scenarios, it has less impact in the network in case of conflict.
Okay.
John, I have some. So one last point regarding the preference. So someone on the mailing list, namely Stefan, has expressed a requirement to be able to, for the operator to express a preference for mapping server advertisements. In the new revised preference rule, so on the right, it's not clear to me how you would take that into account. So I see two options. One is to put the preference in step 2, but this limits the impact of the preference because it is only used if you have the exact same range between both advertisements. And the other option is to put it in step 0, but it's going to impact a lot the network availability if we use guaranteed, because we will not use the biggest range. So we would be back to more or less the old behavior. So how do you want to handle the preference?
So I don't think I can completely answer this yet because we haven't resolved the question as to whether weight is going to be per node or per advertisement. But I think clearly, first of all, you have to decide what this rule says is larger range is preferred, which means any SRMS entry with a range greater than 1 is preferred over a prefix advertisement. So now you have to decide if we're going to incorporate weight, what is the weight assigned to a prefix SID advertisement? When we had the rule on the left, and I actually had a version of this draft prepared, and then we got into the ambiguities with weight, and we didn't publish that version of it. With the rule on the left, it was very easy. You assign the weight of 0 to the prefix SID advertisements, and then the weight of SRMS is whatever was configured, and you put weight at the top, became rule 0. Exactly what happens on the right, I think depends to some extent on both whether we decide it's per node or per advertisement, and then what weight do we want to assign to prefix SID entries? Do we decide prefix SID entries are always, the worst weight, or do we want to pick something in the middle and allow prefix SID entries in some cases to be preferred over SRMS entries? I think that's still an open question.
Yes, but it influences the question you're going to ask to network operator, whether guaranteed with the new revised preference rule is good enough or not. And I don't know if you put the preference in step 0, my answer is no, it's not good enough. So revise with guaranteed.
Yeah, I guess the statement I would make is that if, based upon whatever the input we get, if the decision is quarantine, for example, I think we can figure out what to do with weight. I don't think that precludes either choice.
It does not preclude, but it does influence the answer.
So we're going to have to end this here. Please continue it, in person on the mailing list, wherever is necessary. And I'd like to invite Sanjoy to come forward. Oh. And whoever it is over there who hasn't found their mute button, please find your mute button.
Good afternoon, folks. My name is Sanjay Bardhan from Infinera on behalf of my co-authors, Madhukar, Ramesh, and Jeff, presenting a couple of drafts, primarily trying to address packet optical integration using segment routing. So we presented the O version of this draft in the last IETF. Pretty much, basically, the idea here was to use a concept called transport segments that basically represented optical links in an optical network, and have these transport segments be part of the label stack for in-segment routing. So that was the basic idea, and we introduced another concept called packet optical gateway. Packet optical gateway is a type of node that has the ability to do both packet and optical functions. So that's the interworking function. So in the version, the O version, let me go back to the picture again. The optical links that we show here, we try to represent that as a adjacency SID. So the feedback that we got from the group here was to actually use basically construct the binding SID construct to basically signal the very similar to SRT paths, and this draft is actually a modification that basically indicates that change. We also, we use the Shiva-Balan draft to augment it to signal the POG as well as carry the transport segments. So the next few stuff. So the mechanism is pretty much the same as we presented last. The underlay topologies is learned using usual methods. The POGs are announced using the transport SRPC capability, the sub-TLV. That is part of the Shiva-Balan draft. And then you've got the binding SIDs that basically represent the transport segments. Then we also talked about, this sub-TLV would carry the optical characteristics. We kept that as a TBD right now. Till we figure out if this is good for you, for all of us, we'd enhance the draft to add the sub-TLVs. Basically, what the POG does, it maps the transport segment when it receives an incoming packet and maps it to the appropriate forwarding entry on the optical plane, and then and also it communicates to the PCE, the binding SID, as well as using PCEP-LS, as well as the controller of the PC uses the transport segment to construct the end-to-end path for a given service. So for the extensions here, these are the encodings that we use to declare a POG, a new PCEP type. Basically, and this is just an extension of the draft. It basically is associated with the open object and defines the capability of the device. Then we've got the transport segment. Then encoding is very similar to a TE path binding TLV, and the values are type. This is a new type that's suggested, the length, and then the binding type is defined in the draft itself. A domain ID that basically identifies the optical network that is specific for this transport segment. A binding value, which is the transport segment label, and the transport segment sub-TLV, which is TLV, as we said, which is TVD, as we said. And for non-PCEP extensions, basically the draft has specific encodings for OSPF v2, v3, ISIS, and BGPLS, and it's in the current draft. I'm not going through all of those now. But however, just the POG announcements are specific to the protocol that basically we're enhancing, but the transport segments pretty much follow the same kind of encoding, basically pretty much along the ERO specifications. So the next steps on this is to get consensus on the approach and then codings themselves, and take the next steps and work with the other working groups to incorporate the additions that we talked about. Good. Any questions on this?
I do have clarification questions. Can you go back to slide 2, please? So I'm a packet guy, so maybe I don't understand everything in the optical. My question is, what is the difference between a POG and a regular LSR? Is it they are both part of the same IGP? They have IGP adjacency between A and B?
So a POG is a type of device that terminates packets and puts it into the optical plane, right? So now there are different paths that you get between POG A and POG B. You could traverse the optical plane in different ways, and you could go through different nodes in the network, which is not visible to the packet plane. That's what is being abstracted as a transport segment. So when I'm saying that O1, which goes through BDE, or O2, which goes through BCE in this topology that I'm showing here, O1 and O2 are not visible to the packet network. This exercise is to actually make that possible. So now you, from a overall end-to-end segment routing perspective, you've got the visibility of O1 and O2, and you can include that in the path as you define the end-to-end service.
Okay.
That is the idea.
Okay, but do you have an IGP adjacency between A and B?
No, you don't. You just have B to E, there is an adjacency. IGP knows about B to E.
So you have two different IGPs, one for segment for packet nodes, which are A and F.
A, B, E, F.
Okay, and you have a different IGP.
DNC are not packet nodes in this network.
But what about B and E?
B as in boy.
B as in blue, yeah.
Yeah. B is a packet node.
And it's part of the same IGP as
It's the same
A.
IGP as A.
So it's a packet node,
It is a packet node.
which has interface to the optical node,
It has an interface to the optical node. That's correct.
which is the case typically for all existing LSR. I mean, why do you call it POG?
Oh.
Because existing LSR may use optical network.
Yes, but that LSR, when it connects to another LSR, adjacent LSR, there's just one adjacency that you have. The IGP adjacency is just one. It doesn't see 20 links, and potentially you have 20 optical links, which is not exposed. And this is the way you're exposing it so that you get the end-to-end path.
But that's not true, actually. So why is this case any different to a forwarding adjacency, where those yellow and those paths that you've enumerated there are RSVPT LSPs, for instance?
They're not basically exposed to the packet network.
Right. So if you have a forwarding adjacency between B and E here, that which goes via some other loop, right? It doesn't have to go via a direct interface. It has exactly the same characteristics as these, which is it's a path that goes between those two nodes, looks like that in the IGP, but has various underlying paths. At that point, then we should just be able to use exactly the stuff that I think we already have in SR to be able to advertise this.
So if you have forwarding adjacencies, yes. If you don't, you just expand when you hit the POC. So it's abstracted view of optical network in the foreign segment routing table. So only when you hit POC, you know which optical path, which is not necessarily in any way understood by packet domain.
There are really two planes. You've got the optical plane and you've got the packet plane. The optical plane is running GMPLS and is creating its TLSPs. And you've got the optical plane that and the packet plane that defines the paths between A, B, E, and F. These two guys are not talking to each other today. And this attempt is to basically make sure that you get the paths that the GMPLS folks have actually figured out and propagated up to the packet network. So that now the packet network has one, in one domain can actually include these in their calculations to come up with this end-to-end path.
Maybe I'm missing something, but I see that exactly the same as a packet network that's running RSVP and SR, where the ingress points don't know anything about the RSVP LSPs between two devices.
There's no linking between topologies. You just expose the anchor node where to get in order to get optical bus. Think about multi-layer PC case.
But I think that's the same as if you do, if you advertise a binding SID for an RSVP LSP, you're saying I have a direct adjacency with this guy at the other end.
It's comparable.
Okay,
It is comparable.
So what I'm trying to understand is why do we need specific things in the protocol to handle this differently to the previous
Right
case?
on. So now these optical links have characteristics today that are not part of any PCE calculation when you're doing a packet path calculation. What you're doing here is you're taking these paths, O1, O2, O3, O4, they have potentially different characteristics, optical characteristics, that you may want to push up to a common PCE that's running a common PCE, packet and optical, and calculating the entire path based on constraints.
The same is true for an RSVP LSP, right? So the characteristic of that RSVP LSP, the SLAGs it traverses, all these things
Absolutely.
are exactly the same.
Absolutely.
So what I would like to go back, and I haven't fully read the draft, so I will.
Okay, yeah, we can talk about it.
Is
Sure.
to go back and say, well, why are the things that we've defined to make RSVP LSPs usable in SR, why is that different to what we need here? And then see whether we can just keep the minimum
Sure.
number of things in the protocols.
Yeah, we could do that.
So there's some additional metadata I would like to distribute. Look at the encoding.
Thanks. So again, I'm presenting a similar draft similar to the one that I just talked about. The co-authors are Madhukar, Ramesh, and Jeff. Again, this is pretty much the same thing. Basically, this is just a recap of the stuff. This draft, what it's doing is basically defining transport segment OEM, basically mechanisms to define the liveliness and the service validation across the POGs. So again, as you said, as we saw in the last piece, B and E are the POGs, and the OEM is going to run between B and E to define the liveliness and the service validation. And we'll see some of the use cases, and then go into some of the requirements that we can that this draft lays out. So the first use case is the integrated POG, where the box that is doing the packet and optical gateway function is one. This is the simplest case, but the only constraint here in this case is that these are bidirectional LSPs. That means if one direction is impacted, the other direction must be withdrawn. The second use case is where the packet and optical functions are two disjoint nodes. In that case also, we've got bidirectional characteristics of the links, but we may have to map our signal optical OEM to the transport segment OEM. So that's the two use cases. These are primarily the two use cases that the requirements that I'm going to go through address. There are a couple of other use cases that we have not actually incorporated in the draft, but based on the feedback that we get, we'll probably have to do that, but I'll go through a couple of use cases here. So if you have the POGs connected to another node on the left-hand side, using through some kind of it's dual home with multi-chassis lag, say, for example, then you have the issue of sharing transport labels between the two POGs. So because the link between the route on the left and the POGs is just seen to be one. However, the links that are being monitored by the two POGs are two different things. So they may have to do some link sharing. The other thing that might have to happen is that if one of the links go down, completely go down, there has to be a way for us to signal from POG, say POG A is the top one and POG B is the bottom one. POG A has to signal back into the route on the other end, or signal out to a PC controller that this link is not available. So there are some use cases that we have not taken into account in the dual home POG case. The same thing happens on the Y cable case too. However, there is a concept of active and backup in this case. In the first case, in the multi-chassis lag, you just have one transport label. In the case of in the use case 4, you may have to use two transport labels, one indicating active and the other indicating standby. Because there are two active and backup paths, because this is just a simple Y cable, so you'd be basically sending the traffic to both these guys. One guy would have to be forwarding, the other one would be dropping. So that's the difference here. These are use cases that have not been incorporated in the draft. Depending on feedback, we'll see what we need to do for this. So there's a bunch of requirements. I'm just going to go read through all of them. But yeah, this is very, it's just one by one we'll go through it. Basically, Transport OEM supports both the BFD and the ping function is really the first case. It's on demand and continuous. It must follow the same path as the data plane traffic, must have the ability to exercise any paths that the transport label dictates it to be. And then if you have it has to have the OEM has to have the ability to allow the initiator to add a transport label so that you can control the return path. There's a draft here that is referenced for that may provide the semantics of the return path that may suit the purpose. There's one here. Then you have the transport segment OEM have the ability to initialize from a ingress POG to perform connectivity verification and a continuity check to all the remote POGs within the same optical domain based on the transport segment label. In case of any failure, the transport segment label should have the ability to basically address, send a notification back to the packet domain to withdraw the transport segment label of the affected path and take local protection action. Transport segment OEM should have the ability to be initialized by a centralized controller, should have the ability to be initialized. Once it's initialized, should have the ability to basically receive alerts for local protection or proper informational message. When the transport segment OEM is initialized, it should support node redundancy. That's the last two use cases that we talked about basically refer to this, but we left it at this requirement only. If the primary fails, the secondary must take over without any impact to customer traffic. And then transport segment must have the ability to measure loss, throughput measurement, delay variations, as well as unit direction and didactic measurements. When new paths are initiated, the transport segment label should allow path verification without any noticeable delay. We should be able to actually check for liveliness before we announce the transport segment label. So that could be one of the things that we could do. All these requirements should have no scalability limitations as such. Then transport segment should have a per transport segment label state based on at the originating POG. When the traffic engineering is initiated by the controller, and when the transport is performed by the POGs, there must be a mechanism to communicate these failures to the controller. So the local repair on the optical network takes place, the characteristics of the path may change. And if it significantly changes, then we should trigger a re-advertisement of the transport segment label at the global level. And the formats of OEM ping shall follow the RFC 4379, and BFD should be 5884. So that's pretty much what we had. Get a consensus approach, issue a version of the draft, and work towards the next steps. Any questions on this?
If you have any questions or comments, please keep them short and sweet because we're starting to run late on our agenda. If you don't, I would like to invite the next person to come up, who is, wait a minute. Dave, please.
Could I make a comment on the previous, sorry, I couldn't make it in time to the mic. Yeah, so two quick comments and you can respond on the list. The first one is, why would you want to have a set of requirements on this particular piece of segment routing where you can have generic OEM requirements, right? As opposed to something that is very specific to this particular application. So, why not fold? The second comment is that, I find it interesting that you list requirements including solutions, right? So one requirement is that the solution needs to be LSP ping and BFD in particular cases. So, that sounds, at best odd, and probably more like a reverse engineering of requirements to match the solution that you probably have in mind with the two last requirements. Thank you.
Okay, so if you were in PIM this morning, you got about 10 minutes to do email. Otherwise, here we go. Okay, so what I'm talking about is the draft is a framework for computed multicast applied to MPLS segment routing. This draft was originally presented in Buenos Aires as the 0.0 version. This is a small update of the 0.1. The key progress that's happened, there hasn't been much in this particular draft. Based on feedback, there was a few clarifications added. The key thing is that the corresponding drafts that describe the IGP changes to do this have been published both for OSPF and ISIS. And I'll be doing this presentation again in those working groups during the course of this IETF. Now, as a quick recap as to what this draft is about, for those of you who weren't in Buenos Aires, what we're talking about is the application of computing to determining the routing of multicast segments, which is basically a point-to-multipoint tree in an MPLS-based segment routing network, and how unicast tunnels can be used as part of that multicast tree construction to minimize the overall state. And when I say computing, I'm talking about either the control processor that is in a router that normally does all the Dijkstra's, or potentially an external agent that programs the forwarding planes, such as an SDN controller. The draft itself describes the terminology that we use, for example, the concept of a multicast segment versus a regular segment in segment routing, lays out the overall approach. I discuss loose and specified multicast distribution trees, where the loose tree more or less corresponds to the building blocks for any source multicast, and a specified multicast distribution tree could be considered an engineered source-specific tree, where I've defined a series of waypoints as part of the tree construction. The algorithm is laid out, and there are some fib installation procedures because of this nature of it being hybrid unicast tunnels and multicast replication points. So what we're talking about is an architecture where a multicast tree is the root, the leaves, and where you figure out where the replication points are going to be, and you take advantage of the fact that Spring already has an existing full mesh of unicast tunnels that you can use to interconnect these points. And what's more is this computation can be determined entirely by information that's in the interior gateway protocol. And we've added a couple of TLVs to it to make this possible. Now, there's a number of reasons for doing this, actually. It gives you a whole lot of benefits. The first is there's a minimum amount of messaging to converge the network when there's a topology change, because all of the state to successfully compute multicast trees has already been pre-distributed in the interior gateway protocol. So only the TLVs to advertise the protocol change is the additional information that's needed to fully converge all multicast trees in the network. This reduces data plane state. Because we are using unicast tunnels, to interconnect the replication points, the roots, and the leaves. Certainly in the case where you have sparse trees, the amount of state that you actually install in the forwarding plane of the network is dramatically reduced. So for example, if I had a multicast tree with 1 root and 5 leaves, the absolute worst case, irrespective of network size, would be that 10 nodes needed to install state. And that to me is quite significant in terms of the reduction of the amount of state I need in the forwarding table. We're actually computing minimum cost or near minimum cost trees, so there is a bandwidth saving in the network in terms of using this approach. Because we're using unicast tunnels, unicast recovery will address most failures, which means we're talking about unicast convergence times as far as a multicast service is concerned for most failures. It also allows us to take advantage of ECMP and get some better load spreading if you aren't specifically engineering your multicast trees. And then finally, the big one is this is a direct reuse of the existing MPLS data plane. There is no forklift of the data plane involved here. What we're actually doing is an algorithm that involves tree pruning. And what we do is from the basic shortest path template from the root, the node that is designated the root, to all leaves, you progressively prune down to ultimately determine where the replication points will actually be. Now, like I said, we're trying to produce minimum cost trees because these are ECMP friendly. But what that means is that this is normally a computationally very hard problem. What we actually do is we achieve this with 2 classes of prune. There is a series of pruning steps that we can take that irrespective of the order, we know that if they fully resolve the tree such that every leaf has a unique path to the root, then we know that tree is minimum cost and we don't need to do anything further. There is also, if that does not fully resolve the tree, there's some pruning steps that we would call guesses. And the guesses are actually damn close, but it's one of those, it's kind of like Gödel's theorem. There's always going to be a paradox if there's a guess involved in that there are certain trees that will not resolve. So we need to actually audit the guesses that we made when we fully resolve the tree and go in and apply a fix-up if the guess was wrong. Thing is these guesses tend to be really good. I think it's about 0.03% of the guesses actually require correction. That's based on empirical playing with this. Now we also have the concept of loose and specified trees. Like I said, the loose tree we can construct any source multicast from. The building block is a single multicast segment which uses a SID, an MPLS label. And what it is the root and the leaves are the only things that have been advertised into the IGP, and we use the computation of the multicast tree to fill in all the gaps to connect the root to all the leaves. Now there's also the notion of a specified tree, where what we have done is we've specified the root, the leaves, and all the transit waypoints. And what we do is we do this as a cascaded set of computed multicast segments. So even if the scenario happens where there's a failure in the network that would normally cause things to cross, which could happen if you had sort of a semi-loose specified tree, the fact that we do each one as a unique segment means there actually isn't a conflict. It will resolve itself without looping or duplication. Now, for the IGP changes, it's pretty straightforward. There is, for both OSPF and ISIS, there's 3 additional TLVs required. The first is the capability TLV, which says this node is capable of doing computed multicast, and this is the algorithm that it is supporting. We've designed it so that it would be extensible. We've used an OUI excuse me, algorithm tuple such that different vendors can actually provide extensible versions of their own. We've proposed using the Ericsson OUI for the default start algorithm that we've proposed in the draft. The next is the SID group binding TLV, and that's the one we use for constructing any source multicast, where a node simply says, I'm interested in this group. I want to receive from all senders, or I also want to send to all receivers. And the third is the pin tree descriptor TLV, which is just a very simple list of all nodes that would have a role in terms of constructing an engineered multicast tree. So the role being either a root, a waypoint cross connect, or a leaf. And if you overflow one TLV, you simply use more TLVs because it's just a straight list of items that doesn't need to be presented in any particular order. Now, the next two charts I'll skip because they just go into the details of the TLVs themselves, and these are actually targeted for the other presentations. So what that gets us is to next steps. Now that the IGP drafts have been published, you've got a pretty complete description of the solution that's available for review. So I welcome comments, complaints, suggestions, whatever. Please read the documents and post any feedback that you have to the list. But the only other thing that we needed in next steps is proceeding to interwork this stuff with the existing multicast kit that's out there, such as PIM, etc. That, as it turns out, is fairly straightforward, and we'll probably bring something to the next IETF to describe that. So with that being said, are there any questions?
Robert Rashuk. So I have one question on your last part. How do you plan to glue this into the PIM? Because I was hoping you will not mention PIM in this presentation, but you did. So what's the plan?
Okay.
If the answer would be long, can you take it to the list? If the answer is short, go ahead.
It's going to be a little bit long, so I'm going to suggest we take it to the list. So I'll post something back to you shortly. Any other comments? How many folks have read this?
I read the last version.
Okay, so we have a rather small N here. I'd like to see the N go up. I'd appreciate that. Thank you very much.
Rudiger. Rudiger is next.
So you have to steer the slides because the PDF is not able.
Are you projecting the PDF or the
Yeah,
PowerPoint?
I would say next slide.
Okay.
And,
Okay.
and laser pointer.
Laser should work.
Okay, my name is Raik Leibniz. I work for Deutsche Telekom. Together with my colleague Rüdiger Geib, who also works for Deutsche Telekom, we wrote the draft Leibniz Spring PMS implementation report. And this draft is about ORM use case. And the base for that draft was the draft IETF Spring ORM use case. And Deutsche Telekom has implementation of that PMS. And we use segment routing, but we also have a LDP-enabled network, and we need management plane access to every router to read out the labels. So here we can see how it works. We have there our PMS, which sends a packet steered with the label stick through the network. And with this label stick, the packet travels to the network. First label is 24. It is sent to the router with the label 24. Then it goes to the next router with the label 25, and so on and so on. Okay, next slide, please. Thank you. What we can see here is our measurement topology, or an extract of our measurement topology. We have 3 label edge routers, label edge router 1, 2, and 3. And we connected IPPM conformed Perfas Plus measurement agent to label edge router 1, to label edge router 3. That one connected to label edge router 2 is not shown here. And we also connected the PMS to the label edge router 1 and we compared the measurements of perfast plus, the round-trip delay of perfast plus with the round-trip delay measurements with the PMS. Oh, I forgot to say, can you please go to the slide before? Thank you. We measured the time with the timestamps of the packet, which is steered through the network. When the packet leaves, the time is measured, and when the packet received again, the timestamp is also measured, and the difference is the round-trip delay through the network. Thank you. Please go back to the next slide here. And the second case we also measured is the round-trip delay time between these two remote label edge routers. They are at any point at the network, but not connected directly to the PMS. And we measured the round-trip delay in that time, that way that we send a packet from the PMS over the label edge router 1 to label edge router 2 to label edge router 3, back to label edge router 2 to label edge router 1 and the PMS, and we subtract the round-trip delay from the PMS to the LAR2 from that value, and so we have the round-trip delay between these two routers. And the other way we measure the round-trip delay time is that we send the packet from PMS to label edge router 1 to label edge router 2 to label edge router 3 to label edge router 2 back to label edge router 3, 1 and the PMS. And we also subtract the round-trip delay time from that value with the round-trip delay time from the PMS to the label edge router 3. And so we measured that round-trip delay time in this way. Okay, next slide, please. Yes, this slide is about our measurement setup and the results. So we measured in that way that we send every 10 seconds one measurement packet out of the PMS, and 10 packets were calculated to one mean value, and we measured 8 hours, and after that 8 hours we had 288 measurement values, and we have no ECMP we had no ECMP path at those paths we measured, and the links were not congested, and we proved this measurement with a statistical test named Anderson-Darling key sample test, and this statistical test test whether two sets of data follow the same distribution. That means in our case, if we measured really the same round-trip delay, and when we did the ADK with the originally measured values, the ADK failed, but we did adjustment of the mean and the median value, and so that means that we subtract the constant value from all of the measured values so that the mean and the median of both sets of data are the same. And this is allowed because we aim in measuring the precision and not the accuracy. And with this adjustment, the ADK was below the barrier of 1.993, and so the ADK was successful, and that means that our measurement was successful. So what we can also see that we have a very high precision of the values, because our standard deviation is very small. We also observed a very interesting thing. Can you please go to the slide before? When we measured the delays between the LAR2 and the LAR3 in both ways, we had a constant delay or a constant difference of 10 microseconds. But only with small packets. With bigger packets, this effect wasn't seen. We didn't observe that with bigger packets. Okay. Please go to the next. Yes. We did a further investigation because of this little difference of the 10 microseconds between those measurements. And with our PMS, we had the possibility to vary the destination IP address and kept all other things identical. The MPLS label stack was the same. The measured path was the same. We only varied the destination address. And we have only a few values because this was a little bit more complicated in configuring. Every measurement had to be done with a new CLI configuration. So we measured one IP and then the next IP and the next IP, and we picked those values or those IPs with small and larger mean and median values, and repeated this measurements. And we can see that the destination IP address with ABC.0 was always smaller. The round-trip delay time was always smaller than the round-trip delay time when we choose the ABC.32. And the PMS was, in one case, connected to two label edge routers over two interfaces, so that we can be sure that not only one label edge router causes the difference in that delays. And so we think that we have parallel flows in the forwarding plane in the routers that can cause this difference, but we did not do some further investigations on this. Okay, please next slide. So our implementation and our first experience shows that Spring allows for new ORM features. And theoretically, one PMS is able to measure the whole segment routing domain network. With the Purpose Plus, we need, at every point we want to measure, we need a measurement agent. And with the PMS, we could measure a whole network with only one measurement system. Maybe it is possible to measure some other properties like packet loss or maybe one-way delay. And for us, there is no, or for this, there is no need to standardize some protocols or anything others, because we use only existing protocols like LDP, and so yes, we already talked to Bruno before that this draft maybe did not become an RFC, but the other draft of the Spring ORM use case is stable for a while, and maybe someone wants to join and support this draft. And yes, the last point is now not actual anymore because Bruno already told that the draft Leibniz PMS Spring implementation report will not become an RFC.
So the draft is interesting. Thank you for the draft. Good work. In terms of implementation report, we have a section in the wiki of the working group to detail the implementation report of each or any feature. So I already added a link to your draft. And that's usually the way we publish implementation report, meaning that in general, they are not published as RFC. And for the other draft, which is the ORM use case, we should initiate the last call soon.
Questions, comments?
Yes, I'm Rüdiger Geib. I'm the co-author of the document. I wanted to say two things. In the first slide, it was not quite clear. I think the implementation for now runs on a network which is LDP based. We collect the MPLS topology in an LDP network, but the label stacks which are produced look like those as they would look in an SR domain. So the forwarding we use is like segment routing. And the other thing is, it has been said there is a companion document, the ORM use case draft, and this should go to workgroup last call. And we would be really happy if there are at least one or two volunteers reading the document, providing comments to the list in order to finalize the workgroup last call. Thank you.
Ahmed Bashandi, Cisco Systems, very nice work. I would like to suggest a couple of extensions. First extension is to try to do this testing for layer 2 link aggregation groups. Basically, there is already a draft that's in last call to be able to direct traffic towards a particular link. The second comment is to try to apply the same procedure using the segment routing IPv6 forwarding plane. You're using MPLS forwarding plane. It would be great to do the same thing with IPv6 forwarding plane. It's just a routing header.
So I'm not sure if it is possible to do it in the IPv6 header to let the packet circle is possible.
You can. There are in 6man. There are Stefano Previdi has a few drafts. There's actually one draft that describes exactly how to do that.
Okay.
Rüdiger Geib again. That's nice. I mean, we would like to do that, but our test network, our laboratory network is simply an LDP-based MPLS network, so we cannot. Sorry.
Yeah, it's going to change soon.
All right, so proof of transit and inbound OEM. So we are doing, and by the way, if you've been to SFC earlier on, this is very similar. So you might want to go and take an early break. But if we're doing kind of segment routing and steering traffic down a particular path, I think the one question that we've barely answered ourselves so far is how can we actually prove that the traffic is actually following the suggested path? And by proving, I mean proving in a cryptographically secure way. And that use case was brought to us by one of the co-authors that we have, Steve Ewell, who works for a bank. And they have that particular problem that they receive feeds from multiple upstreams, and they have to make sure that the traffic goes through a sequence of firewalls and whatever. Now, that's relatively easily done if you're in the physical world. You can check the cabling, you can put probes between the boxes, all fine. But as you move to NFV, single vSwitch configuration blows the overall system. So how do you do that? And so he, well, worked, and we try to come up with a solution. So what we want to go and make sure is prove that we have a path that is the preferred path, or the path that the traffic should go, which is ABC. And so it shouldn't go AXC or whatever. And the other thing that we need to make sure is that we can decouple the domain where the thing is applied to the domain where the thing is verified. So you typically have a domain or an operational environment that is even controlled by a different group where the verification should need to happen, and you have a trust domain A where the thing is applied. Now, we've been looking at a multitude of different approaches, and well, the one thing that we came up with, or that is kind of common to multiple approaches, is you have a secret. You split the secret into as many nodes as you have in the system that you want to go see verified, not necessarily all the nodes, but the nodes that you want to see verified. And then while the traffic travels through the network, you pick up these individual pieces and see whether you can reconstruct the pieces into the original secret later on or not. So if you have your pie, and the pie is split into 3 pieces here with 3 nodes in that service chain, then, well, you can either reconstruct the pie at the very end, make it a full pie, or you can't. If you can't, then something wrong happened, and that's an indication for something going wrong. Now, we can't split pies here in the real digital world. We want to go take something else. What we're taking is polynomials. And so we're going all the way back to school math, and the base schema that we had there is, we know that a polynomial of degree n is defined by n+1 points. So line, 2 points, parabola, 3 points, and so forth. And it's uniquely identified by these 3 points. Out of 3 points, I can, using Lagrange interpolation, I can always go back to the original polynomial. Now, we don't take the pi as a set, we take a polynomial. And we take a polynomial of degree n for n+1 service hops. So example here, 3 hops, we take a polynomial of degree 2, take 3 points on that curve, and now the shares of the secret that we want and that we dedicate to every single node are these individual points. And as we traverse through the network, the packet's going to go pick up these points. And then at the end, we can either interpolate the original polynomial again and check, done or not. If you operationalize the overall thing with Shamir secret sharing, it's operationally very effective and can be done computationally very cheaply. It all boils down to 3 additions, 1 multiplication, and 1 modulo prime operation at every single hop, which is why it's far cheaper than things like nested encryption, for instance, that people also come up with as an idea. So that's why we went down that path. If you fully operationalize things, you would say, well, Frank, you got to go and dedicate now a polynomial per packet. How do you go provision this? Because you need a load of polynomials that way. So what we ended up doing is not take 1 polynomial, but take 2. 1 that we keep relatively constant, i.e. for years eventually, and 1 that we do on a per packet basis. And the sum of these 2 will be the thing that we operate on. So 1 is on a per packet basis, it's making the packet unique, and it is public. And the other one we keep secret. The combination of secret and public will be something secret again. We're not really passing on the entire polynomial in the packet, by the way. We're only passing the constant coefficient, which is good enough. Now you can ask the question, so how much metadata do you need to carry in every single packet in order to allow for that schema? The question is, the answer is it depends, as usual, right? So if we dedicate ourselves something like 64 bits of metadata, then, well, you can have 2 to the power of 64 independent coefficients to construct your second polynomial, your public one. And that means if you're running, say, a 100 gig line rate, you can survive for roughly 3,100 years. That's a relatively long time. If you take less metadata, well, you have less room to play with. And so at 100 gig and only 32 bits of metadata, then you're only surviving 22 seconds, which means you've got to refresh the polynomials more frequently. Well, carrying the metadata, I think what we have as a prototype implementation right now in FIDO VPP together with Open Daylight as a controller. That's been built, and we're using 64 bits for now. And well, we can carry the metadata in a variety of transports. One is obviously segment routing, and which is why we're here. So carrying that means we need another TLV in the segment routing header. So thanks to you guys, you've moved from policy elements to TLV format, so we can throw anything in there, and we'd love to throw this metadata for proof of concept in. That's why we're here, as I said. And then we can go and distribute that metadata to the individual nodes and run with it, right? So as I said, we have a prototype implementation of this whole thing. Now, if you take things into a slightly broader perspective, this hints or kind of points the way of a more generic principle, i.e. in-band OEM. And I'm just presenting that as a kind of FYI here. There's a larger presentation in the routing working group on Wednesday. Just from a principle perspective, what we're doing here is path verification, but if you're carrying along additional metadata into the packet, like node ID, ingress interface, egress interface, sequence numbers, timestamps, all of that can be squeezed into metadata into the packet. You can do other crazy things like verify ECMP networks, derive a traffic matrix, look into kind of if you have overlay and underlay, what happens in an overlay if you're spanning multiple networks, look into, well, whether the traffic is really following the principles that you're supposed to, that you're imposing on the traffic. You can even put metadata in like GPS geolocation and then implement policy based on GPS geolocation in the packet. So i.e. don't go through a particular country or don't accept traffic from a particular country. So ends all out into squeezing some information between the original header that we had or an extension of the original header and payload. And where you place it is really up to you. In V6, you can use an extension header and VXLAN GPE. You wouldn't use another protocol header. We talked about SRv6. NSH, another option, which is why, well, if you've been to SFC earlier on, you've seen the very same pitch already. And how does it work? Well, it's always following the same principle. You end up at a domain edge or at a host with just a header and payload, and then you're adding another blob between the header and the payload, and that blob better be constant. So it better be domain specific and fixed for the domain so that you don't end up with path MTU issues like we had with route recording, similar thing back well, 30 years ago in 791 and the likes. And that array, along with maybe fixed information like we use for proof of transit, is then incrementally populated. Here we just use the example of node ID and egress interface, and you populate the stack throughout. And at the very end, you spit the overall thing out, maybe as IPFix. That's what we do in the prototype right now. That can be then used for post-processing or spit it into Kafka or whatever. So any big data, you do it on us. That's the concept in a nutshell. We'd obviously, well, appreciate your feedback. I already heard from Stefano that if you want yet another TLV, it's going to go through 6-man and not to Spring. But if you guys nod and say that's a good idea, then maybe the debate is a little easier in 6-man. Any thoughts? It's too late in the day, right? Yeah. There's somebody finally kind of moving.
Hi, this is Rüdiger Geib again from Deutsche Telekom. I'm not quite clear. Are you looking for support for that in backbone networks also, or is it mainly data centers and SFC?
Well, if you want to go do that in your backbone, I wouldn't stop you from doing that. Okay. So right now, I think the main applicability that we see, so we have mostly a software implementation. It's mostly applicable or where the story started, and that's why I put the initial story out, is mostly in the NFV land, where you have virtual appliances, where you have services or service chaining with virtual appliances. And the other domain where we see it really apply is network overlays. And those might be kind of network overlays that carry or span multiple carrier networks, where you as the backbone carrier don't even see the traffic, but people are still kind of overlay hop by overlay hop, looking whether, say, certain things are in place or not, right? So it's more like one layer up from core transport, but if you want to go push for that in core transport and want to make everybody change the ASICs, fine.
That is what I would
not
like
a bad
to
idea. might go kind of stir up the overall industry a little. And in network processors, we've proven to do that. Even sophisticated ASICs can do that, but if you go with vanilla ASICs, they already struggle if you want to insert something between the header and the payload.
I'm not sure whether the draft makes that really explicit. I read into a few documents. Maybe I've overread that section, but it would be great if the draft say, well, this is for these and that kinds of network.
Fair point.
Mainly.
Yeah, it's kind of the 00 thing right now, and it's a little rough on the edges. I understand that. There will be more polishing, and you're happy to help me polish.
Everybody wants help polishing.
Yeah, I know.
I do too. So since nobody else is at the mic, I'll be lazy and remain seated. Between tapping your toes and waving your hands and me not having read the draft, I'm not sure I understood anything, but do I correctly understand that you need a different secret provisioned per distinct path through your network that you want to be able to audit?
Yes.
Okay.
So
Thank you.
the service path is uniquely identified by a secret, or the other way around. So you have a secret per service path that you want to go refresh at times if the second polynomial is used up. Yeah, that's correct. And that goes well with a service chain identifier or something similar. If you have one.
Maybe not so well if you want to generalize this technique to any arbitrary use of paths through networks.
If it's any path, then yeah, then it would be any identifier, and then you can have many of those. I agree. Quite a few. So don't do that per flow, please. All righty, thank you.
And with that, we are finished early, a little bit. Do we have the blue sheets? And if somebody can bring the blue sheets forward, that would be great, or, wave them around or something. Whoa. I've not once gotten to use the big red button yet.
No.